We don't know the answers to a lot of questions. For example, how many alien societies exist and are detectable? Even though we don't know how to answer such a question, we can at least try to figure it out with a little help from our beloved math. First, we have to have a pretty good idea about how the universe works, and of course about the star and planetary formation, as well as conditions for life as we know it. This means we have to study and collect a lot of data. Luckily for us, we humans aren't so bad. Physics, astronomy, chemistry, biology, and all natural sciences offer us the hints for the mathematical set of parameters that will give us an equation to calculate the number of alien societies that exist and are detectable. Second, one has to sit down and think about which parameters should appear in the equation and which not. Do you think it's difficult? I think so. But luckily for us, in 1961, scientists Drake came up with a famous equation that estimated the number of transmitting societies in the Milky Way galaxy. Follow me to know more about the Drake equation, and I promise you will not regret it. Are there civilizations out there listening? We don't yet know the answer, but Dr. Frank Drake, president of the SETI Institute, came up with an equation that allows us to make an estimate by multiplying 7 quantities related to the prevalence of life. Before getting into it, here's some historical context. Drake organized a historic meeting at Green Bank in November 1961 to discuss what would soon be called SETI, the search for extraterrestrial intelligence. Most sources agree that 10 individuals attended this meeting, including Drake himself, and in particular, Philip Morrison, Carl Sagan, was both in attendance. Drake said that he came up with the equation a few days before the meeting, largely as a way to come up with an agenda. Each term in his equation was meant to serve as a discussion point for the attendees. Now we don't know precisely the form that Drake wrote down at the meeting, but the canonical formalism was first published by Drake in 1965. After the original meeting, the participants dubbed themselves the Order of the Dolphin, inspired by attendee John Lilly's research on dolphin communication. The meeting and equation were even commemorated at Green Bank with their plaque, which is still there and worth checking out if you like astrotourism. Clearly then, there was a sense that this was a rather historic meeting. But what exactly is the Drake equation? The Drake equation estimates N, the number of transmitting societies in the Milky Way galaxy. Let's take a look at it. The terms are defined as follows. N equals the number of civilizations in the Milky Way galaxy whose electromagnetic emissions are detectable. R star equals the rate of formation of stars suitable for the development of intelligent life, number per year. Fp equals the fraction of those stars with planetary systems. Ne equals the number of planets per solar system with an environment suitable for life. Fl equals the fraction of suitable planets on which life actually appears. Fi equal to the fraction of life-bearing planets on which intelligent life emerges. Fc equals the fraction of civilizations that develop a technology that produces detectable signs of their existence. L equals the average length of time such civilizations produce such signs in years. Currently, there are 100 scientists at the SETI Institute working on nearly 100 research questions. But each of these topics can be related to one of the terms in the Drake equation. Looking closer, the anatomy of the Drake equation can be grouped into just 3 types of variables. We have a rate as the first term that has units of inverse time. For example, the rate of stars is x per century, or y per year. It tells us how many stars are forming in the Milky Way in a year or in a century. Next, we have a bunch of fractions and numbers and quantities without any units. Okay, Since we have a rate multiplied by a bunch of numbers, then the first 6 terms must all represent a rate when combined. But the Drake equation calculates n, and n isn't a rate. To get rid of the rate, we have to multiply by a time, which in this case is L, the mean lifetime of civilizations. That's all. Simple, elegant, the Drake equation. But can we say something more? Of course we can. Can you see what's the problem with the equation? I bet you see it. The problem is, what are the parameters' values? Of course, we can go ahead and plug in guesses for these values, and that's actually what the original attendees did, arriving at a final estimate of n between 1,000 and 100 million. But let me emphasize in the clearest possible terms, those are just guesses, J. Our problem is that it's not possible to evaluate the formula in a conventional sense, because we simply don't know the values of most of these terms. Humans are ignorant. We have to deal with that. As we said, we don't have all the answers. We have just a few of them. In the case of the Drake equation, we don't know the values of the terms, and anyone can guess, and your guess is as good as mine. Even a child can use it, and here we have a recipe for disaster. We end up with a situation where lots of people can come up with their answers and claim them as a result. There have been enough previous studies on this topic to fill a small hoard of hard drives in many ways. The Drake equation is a victim of its own success. It seems that every month or so, we hear about a new study that plugs numbers into the equation and arrives at a different answer. None of this teaches us anything, because at the end of the day, we still don't know most of the terms. Even worse. Also, the press releases in particular give the public a false sense that we know the answer, or that these arbitrary estimates somehow represent evidence. The real thing is that we just know the first 2 numbers in the Drake equation, R star and FP, but that's about it. The rate of star formation is something we can absolutely measure and pin down through the detection and study of young stellar objects. We can estimate that the current rate of star formation is about 2 per year. The fraction of stars with planets is also eminently observable, and recent estimates from Kepler and microlensing studies suggest that it's close to 1. Planets seem to be a natural byproduct of star formation. The next term is the average number of planets around each star capable of supporting life, and this is where we enter terra incognito. Take, for example, our solar system. There are numerous definitions of the habitable zone that lead to anywhere from 1, just the Earth, up to 3, Venus, Earth, and Mars. But clearly, Venus is pretty different from Earth. Yes, maybe it might be possible for it to support life, but intelligent life? We don't know. Our surveys can count how many Earth-sized planets are in the habitable zones of their stars. We have no way with these surveys, at least, to distinguish between Venuses and Earths, or indeed, presumably other types of planets that we've simply never seen before. And this doesn't even touch on other criteria, like plate tectonics, obliquity, magnetic fields, etc. So really, we don't know this number, but we can actually make progress if we just redefine it. If we consider it to be the number of Earth-sized planets in the temperate zone of their stars, that's tractable. That's a number we can potentially measure. But by casting a large net like this, we would end up making the other term smaller, since it's now defined over a wider span of worlds. But at least this makes n an observable quantity. Having said all of that, we actually can't even agree on how many Earth-sized planets are in Earth-like orbits anyway, with modern estimates from the same data set varying by a factor of 100. Nevertheless, in principle, this is a number that we can hope to measure with near future surveys. Now, as we move on to the subsequent parameters in Drake's equation, our ignorance only gets worse. The uncertainty here is so extreme, it's not even possible to define it in a meaningful sense. So any calculation you see about the Drake equation has very simply guessed all of the terms except for maybe the first two. The perpetual torrent of articles claiming to estimate n in the Drake equation has frustrated and exacerbated many astronomers to the point where now, where they see such articles, many astronomers either ignore them or actively disparage them. The Drake equation has been abused so many times with the media circus being dragged out and glammed up for another round of misleading headlines. Nowadays, the Drake equation is now often marked and ridiculed in many academic circles. Many astronomers not only don't trust the Drake equation, they really hate it. But here's the thing. Yes, there are undoubtedly flaws with the Drake equation, but much of the bad reputation that it offers is a product of its past abuses and not its original formulation. All of this is undoubtedly largely fueled by the media circus that tends to come along for the ride. In the last part of the video, we try to provide a list of the most reliable estimates of the parameters that appear in the Drake equation. Our star, the star formation rate in the Milky Way. The most recent calculations by NASA and ESA indicate that the current star formation rate in our galaxy is 7 stars per year. FP, the fraction of such stars that own planets. Recent research on exoplanets has shown that 40% of Sun-like stars have planets, and the real fraction could be much greater, as only considerably more massive planets than Earth can be detected with current technology. The Kepler mission of NASA started on March 6, 2009. It should provide an estimate more accurate in the number of planets per star located in a habitable zone. In fact, it can count on instruments much more sensitive than in the past, capable of detecting planets as large as the Earth with orbital periods of up to 1 year. Even if we know the number of planets that are in the habitable zone, however, determining how many of them have the right combination of factors can be difficult. Furthermore, if the hypothesis of the rarity of the Earth is valid, the set of characteristics verified on Earth may not be common at all, and the number Ne could be extremely low, tending towards 0. FL, the fraction of them that actually develop life. We don't know very much about it. It must be greater than 0.13 on planets older than 1 billion years. Fi, the fraction of them that actually develop intelligent life. This value remains particularly controversial. Those who speak out in favor of a low value point out that of the billions of species that have existed on Earth, only one has become intelligent. Those who are in favor of higher values emphasize instead that the complexity of living beings tends to increase along the course of evolution, and conclude that the appearance of intelligent life, sooner or later, is almost inevitable. FC, the fraction of them that is able and decides to communicate. Although much speculation has been made, no concrete data is available on this parameter. L, the average duration of the communicative phase of each of these civilizations. Some values were proposed, 420 years, 304 years. Others, such as astrobiologist David Grinspoon, have suggested that once a civilization had developed, it could overcome all threats posed to its survival, and then survive for an indefinite period, bringing L to the order of billions of years, values based on the quoted estimates. R star equals 7 per year, FP equals 0.5, Ne equals 2, FL equals 0.33, Fi equals 0.01, FC equals 0.1, L equals 10,000 years, gives a result of N equals 7 times 0.5 times 2 times 0.33 times 0.01 times 0.1 times 10,000 equals 23.1 Existing extraterrestrial civilizations capable of communicating in our galaxy. Drop a line below so we know if this is the result you expected